Hi everyone, I'm Nick. I work for the GAMMA and Telepresence research groups, and today I'll be presenting shared haptics and skeletal reconstruction in social VR training simulations. So a quick overview of what we're trying to do. We're trying to integrate all of these individual points into some immersive training simulation such that a virtual simulation can be used to train somebody to do something real, such as a surgery. We want to have shared passive haptics, so some object that is physically real feels the same way for both, for anybody in the scene. We want complex interactions like physics to be very accurate between people, so there's no discontinuity there. We want to use skeletal reconstruction to best portray what people are trying to do physically, like move their hands or their bodies. We want to distinguish hands from controllers that we usually use so that there's more of a personal feeling to interactions that you're having in the scene. And we want to have complex interactions with things like cloth or other complicated objects that we can have. So just a quick overview of the state of the art. This is what people look like in virtual scenes at the moment in commercial products like AltSpace VR or Rec Room. As you can see, they're not the most accurate human representations. They're lacking a bit of expression and personality. And really, based on their hand motions, it's kind of hard to tell what they're trying to portray, right? So some quick motivations of why we're trying to do this. We commonly hear in VR, I can't see my arms, my legs, my hands. Why is the simulation so inaccurate? Also, we're moving to a social VR era. I'm sure many of you have seen the Facebook Spaces demo. So we have to figure out ways to represent people accurately in these kind of scenes. We also want to have accurate simulations that require strong interpersonal connections, like surgery, where the doctors have some strong relation to the nurse or other assistants. We want to make social VR less awkward or silly. We don't want people throwing body parts around as we see in many of these demos. And we want to deal with the problem that calibration between different VR systems may not be consistent, even if they're in the same space. I'm going to introduce the devices that we're going to be using. The Htc Vive uses two lighthouses, which are little boxes that transmit infrared signals. It can track up to about 15 by 15 feet. And because the lighthouses are not connected to a specific computer, the headset and the controllers are responsible for tracking themselves. We can have multiple of these in the same area. With the only limitation being occlusion, we have to make sure that people are not standing in front of each other. The Kinect version 2 is a box-like thing, I guess. It's a depth sensor that uses computer vision techniques to create some depth cloud that can be used, or a point cloud that can be used for reconstruction, or it can be used to figure out the human skeleton. But it can't possibly do toes or fingers, which is why we have the leap motion, which is specifically designed to do fingers and hands. So with all these devices, we're going to see what we can do in a social VR simulation. You'll notice that there is a lack of Kinect throughout the presentation. It's because we're not quite there yet. So the main scenario that we're trying to portray is a surgery simulation. Tools will be shared between people, and these tools will be necessary to reach the goal. We want to assign roles to different players, such as nurse, doctor, body bagger. And we want to see if how well people fall into these roles with the different aspects that we mentioned before. And the assumption here is that the reconstruction is not as important as the interaction. So the bodies are fairly simple right now. So an example would be the surgery room. I've been told that it looks more like a torture chamber. I'm working on making it more like a surgery simulator. And I was partially inspired by this demo, which is a laparoscopic surgery done with the Htc Vive controllers. Our setup looks like this. So we have some passively haptic body and a table. It appears in the same place for both people. We have two different Vive headsets and two controllers per headset. And on the front of the headset, we have a leap motion, which is used to reconstruct the hands. I'll show you a demo before I explain what's happening. So here, two people are interacting in the scene. For half of the video, they're figuring out how to actually interact with each other. And now they, because of the physical correctness of the two different headsets, they're able to share controllers. The person in the blue shirt asks the other person to cut some cloth so that they can throw the heart into the chest, which is how surgery works. And the other person does it for him, and so the heart can go into the body. And so this is a very basic idea of what we're trying to do. We're trying to have collaborative, goal reaching. But hopefully not like that. So, what? Okay. Just give me a second. Yeah, it seems that way. Okay, it's fine. I'll explain it. It was a nice video, though. So first we have to calibrate the two tracking areas. The server has to figure out where its own lighthouses are in the space of the game, which may not be the same for both players because Steam VR, which is a software used to calibrate the HTC Vive, dynamically figures out where the center of the area is, where its forward vector is, those kind of calculations. So the server figures out where its own lighthouses are. It chooses one for the client to calibrate to, and it tells the client where this lighthouse is. The client figures out which of its own lighthouses corresponds to the server's. It positions some lighthouse to be where its own uncalibrated lighthouse is. It attaches itself to create a pivot, and then it moves its own lighthouse to where the server's is. And this is why I had a video. Maybe if I have time, I'll bind it later. Yeah, I just thought that would be time consuming. I'll do it. Just give me a second. This is arguably my fault. What? Isn't Google great? Yeah, I guess not. I'll try one more thing. This won't take too long. My presentation's not that long. I can type really fast. Yay. Okay, here's what I'm talking about. So I will explain step by step. With visuals, this should hopefully make more sense. So the server queries its own physical lighthouse locations. It chooses one to calibrate to. The client figures out where its own lighthouses are with respect to the game space. It figures out which one corresponds to what the server wants to calibrate to. It attaches itself, and then it moves itself into place. Yep. What? This is great. I love Google. So then we have to do frame-by-frame networking. There are quite a few things that need to be networked correctly for the simulation to feel accurate for both people. There are static objects that are not necessarily interactive with, or that don't really have any kind of physical interaction. Or, they're not affected by physics and they're not too dynamic. such as controllers, your head, body parts or clothes if you're like an avatar. There are bone transforms for hands or other body parts that we want to be physically accurate. And then there are physics-based objects such as cloth, body parts that you might want to throw around, other virtual unowned objects, which I'll explain later, and maybe some tools. And so what happens is that the server or the owning client, they figure out where, or they portray to everybody else where these updated positions are, assuming that they have direct control over this object, which I will explain in the next slide. Come on, Google. There we go. So what I mean by unknown physics is at the bottom. So we're trying to network physics. This is a well-known problem in all kinds of game design. Usually it's solved by just letting physics be asynchronous and not a game mechanic. We can't do that because we want the interaction to be realistic. So what I do is I make it such that the last person who interacts with the object is the one who gets to say where it is next. And so that person becomes the owner of the object, and the result is that the physics is networked correctly, it's highly accurate, there's a little latency because multiple people are not fighting over where a single object is. So some limitations of my system. My calibration is heavily limited by whatever Steam VR decides the calibration is. This is especially important for the floor, which uncalibrates itself if you put a table or some other big object into the into the physical space. Currently, my simulation only supports 2 players. I want it to support up to 4, but there are many, many wires involved. And finally, the Leap Motion is not the smartest device in the world. It gets confused. You can trick it into thinking that you have 3 hands. So some extended possibilities that we want to explore. This right hand is the Leap Motion hand. This is whatever the Kinect decides to spew out. We want to merge these such that we have full body reconstruction. So some other applications that we were looking at are maybe construction, sports like ping pong, fencing, sports that don't require a huge area. The possibility of telepresence or meetings that require, hand gestures, facial expressions, things like that, and maybe education. Applications that require a lot of interpersonal relations. That's all I had. Thank you.